When installing a 75 kVA 480/208 volt three-phase transformer, and the secondary current is 208 amps, you might wonder about reducing the neutral conductor size. The question revolves around whether you can reduce the neutral conductor size if it's only carrying the unbalanced current. The National Electrical Code, or NEC, specifically Article 220.61, addresses this scenario. It states that the neutral conductor size can be reduced to a minimum of 1/3 the size of the phase conductors, provided certain conditions are met. This applies to systems where the unbalanced load exceeds 200 amps. In this particular case, the secondary current is 208 amps, which exceeds the 200 amp threshold. Also, the neutral is only carrying the unbalanced current. Given these circumstances, reducing the neutral conductor size is permissible. For instance, you could use a 3/0 neutral conductor alongside 3 4/0 conductors for the phase conductors. This reduction in size can be advantageous because it allows all the necessary conductors, including the grounding electrode conductor, to fit within a 2-inch GRC conduit, thereby simplifying the installation process. To elaborate further, let's delve into the conductor sizing calculations. Firstly, for the phase conductors, we have a current of 208 amps. Assuming you're using 4/0 THHN copper conductors, which have an ampacity of 0.778, we calculate the required conductor size as 208 amps divided by 0.778, which equals 267.37 kcmil. Secondly, for the neutral conductor, since we're reducing its size to 1/3, we divide the current of 208 amps by 3. Then we divide that result by 0.778, the ampacity of a 3/0 THHN copper conductor, which equals 89.12 kcmil. As for the grounding electrode conductor, a number 2 conductor is generally sufficient. Now, let's consider the conduit size. Based on the conductor sizes we've discussed, a 2-inch GRC conduit should provide adequate space for the following configuration. This includes 3 4/0 THHN copper conductors for the phase conductors, 1 3/0 THHN copper conductor for the neutral conductor, and 1 number 2 THHN copper conductor for the grounding electrode conductor. However, before proceeding with any changes, it's crucial to verify the actual ampacity of the conductors. This verification should take into account the specific insulation type and the operating temperature, as these factors can influence the conductor's ampacity. Moreover, it's essential to obtain approval from the local electrical authority before implementing any modifications to the electrical system. Local regulations and codes may have specific requirements or restrictions that you need to adhere to. Reducing the neutral conductor size can offer practical benefits, such as easier installation and reduced material costs. However, it's vital to ensure that all applicable codes and standards are followed to maintain safety and compliance. Always prioritize safety and consult with qualified professionals to ensure the electrical system is installed correctly and meets all necessary requirements. Remember, electrical work can be hazardous, and it's crucial to take all necessary precautions to protect yourself and others from potential hazards. By carefully considering the factors outlined above and following all relevant codes and regulations, you can safely and effectively reduce the neutral conductor size in your 3-phase transformer installation. To summarize the key points, firstly, the NEC allows for reducing the neutral conductor size under specific conditions. Secondly, the neutral conductor can be reduced to a minimum of 1/3 the size of the phase conductors when the unbalanced load exceeds 200 amps. Thirdly, verify the actual ampacity of the conductors based on insulation type and operating temperature. Fourthly, obtain approval from the local electrical authority before making any changes. Fifthly, ensure all applicable codes and standards are followed. Remember to always prioritize safety and consult with qualified professionals. Considering the specific parameters of the 75 kVA 480/208 volt 3-phase transformer, let's further refine the calculations and considerations for reducing the neutral conductor size. The secondary current of 208 amps serves as the basis for determining the appropriate conductor sizes for both the phase conductors and the neutral conductor. As previously mentioned, The NIC, specifically Article 220.61, provides the guidelines for reducing the neutral conductor size. However, it's crucial to understand the underlying principles behind this allowance. The primary reason for allowing a reduced neutral conductor size is that in a balanced three-phase system, the neutral conductor theoretically carries little to no current. This is because the currents in the three-phase conductors are equal in magnitude and 120 degrees apart in phase, resulting in a vector sum of 0 at the neutral point. However, in reality, perfectly balanced loads are rare. Imbalances in the load distribution among the three phases can cause current to flow in the neutral conductor. This unbalanced current is what the neutral conductor must be sized to carry. Therefore, when reducing the neutral conductor size, it's essential to accurately estimate the maximum unbalanced load that the neutral conductor will be subjected to. This estimation should take into account the types of loads connected to the system, their individual current draws, and their distribution among the three phases. In situations where the load is primarily linear and balanced, the unbalanced current will be relatively small. However, in systems with significant nonlinear loads, such as electronic devices with switching power supplies, the unbalanced current can be considerably higher due to the presence of harmonic currents. Harmonic currents are multiples of the fundamental frequency of the AC power system, typically 60 Hz. These harmonic currents can create significant current flow in the neutral conductor, even if the fundamental frequency currents are balanced. Therefore, when dealing with nonlinear loads, it's crucial to carefully analyze the harmonic content of the load current and ensure that the neutral conductor is adequately sized to handle the harmonic currents. In some cases, it may be necessary to upsize the neutral conductor beyond the minimum 1/3 of the phase conductor size to accommodate the harmonic currents. Furthermore, the type of wiring system can also influence the neutral conductor sizing. In a separately derived system, such as a transformer, the neutral conductor is typically bonded to ground at the transformer. This bonding creates a low impedance path for ground fault currents, which can help to quickly clear faults and minimize the risk of electrical shock. However, this bonding can also result in some current flowing in the neutral conductor, even in the absence of an imbalanced load. This current is due to circulating currents caused by differences in ground potential between different points in the electrical system. Therefore, when dealing with a separately derived system, it's important to consider the potential for circulating currents and ensure that the neutral conductor is adequately sized to handle these currents. Returning to the specific case of the 75 kVA 480/208 volt three-phase transformer, let's examine the conductor sizing calculations in more detail. As previously calculated, the phase conductors require a size of 267.37 kcmil based on the 208 amp secondary current and an ampacity of 0.778 for 4/0 THHN copper conductors. This calculation assumes that the conductors are installed in a raceway or conduit and are subject to the ampacity directing factors specified in the NEC. The NEC provides tables that list the ampacities of various types of conductors based on their insulation type, size, and installation conditions. These tables also specify directing factors that must be applied when multiple conductors are installed in the same raceway or conduit. The directing factors are intended to account for the heat generated by the conductors, which can reduce their ampacity. Therefore, it's crucial to consult the NEC tables and apply the appropriate directing factors to ensure that the conductors are adequately sized for the intended application. In the case of the neutral conductor, the calculation yielded a size of 89.12 kcmil based on the 1/3 reduction and an ampacity of 0.778 for 3/0 THHN copper conductors. However, as previously discussed, this calculation assumes that the unbalanced load is relatively small and that harmonic currents are not a significant factor. If the unbalanced load is expected to be significant or if harmonic currents are present, the neutral conductor size may need to be increased. To determine the appropriate neutral conductor size in these situations, it's necessary to perform a detailed load analysis and harmonic analysis. A load analysis involves determining the maximum current draw of each load connected to the system and calculating the resulting unbalanced current. A harmonic analysis involves measuring or estimating the harmonic content of the load current and calculating the resulting harmonic currents in the neutral conductor. Based on the results of these analyses, the neutral conductor size can be adjusted accordingly. In addition to the conductor sizing calculations, it's also important to consider the voltage drop in the conductors. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC specifies maximum allowable voltage drop limits for various types of circuits. To minimize voltage drop, it's important to select conductors that are large enough to carry the load current without excessive voltage drop. The voltage drop can be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance of the conductor. The resistance of a conductor depends on its material, size, and length. The NEC provides tables that list the resistance of various types of conductors. Therefore, it's possible to calculate the voltage drop for a given conductor size and length. If the calculated voltage drop exceeds the allowable limits, the conductor size must be increased. Finally, it's important to consider the grounding requirements for the transformer and the electrical system. The NEC specifies detailed grounding requirements that must be followed to ensure the safety of personnel and equipment. Grounding provides a low impedance path for ground fault currents, which can help to quickly clear faults and minimize the risk of electrical shock. The grounding electrode conductor connects the electrical system to the earth, providing a reference point for voltage. The size of the grounding electrode conductor is determined by the size of the service entrance conductors or the equivalent. In the case of the 75 kVA 480/208 volt three-phase transformer, the grounding electrode conductor is typically sized according to NEC Table 250.66. As previously mentioned, a number 2 grounding electrode conductor is generally sufficient for this application. However, it's important to consult the NEC table to verify the appropriate size based on the specific installation conditions. In summary, reducing the neutral conductor size in a three-phase transformer installation requires careful consideration of several factors, including the imbalanced load, harmonic currents, wiring system, conductor ampacity, voltage drop, and grounding requirements. By performing detailed load analyses, harmonic analyses, and voltage drop calculations, you can ensure that the neutral conductor is adequately sized to handle the expected current flow without compromising safety or performance. Remember to always consult the NEC and local electrical codes and to seek guidance from qualified electrical professionals to ensure that the installation is performed correctly and safely.